Hello and welcome to lesson number 7, Polynomials. So we actually discussed about polynomials previously in the functions episode, but of course we're going to be doing it again in this episode here. So any polynomial function is a function that is of this form. A function fx that is of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus dot 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 all the way down up to plus a2 x squared plus a1 x to the 1 or simply ax plus a0 times x to the 0 and x to the 0 is 1. So we have just a0. So this is a polynomial function. In here all the numbers a sub n and a sub n minus 1 dot 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 all the way down to a2, a1 and a0, all of these numbers are real numbers. They are real constants. So they are elements of the real numbers and they are constants. And then all of these n's are integers, positive integers. So we need n to be an element of the positive integers inclusive of 0. The reason inclusive of 0 is included here is because it is possible for a polynomial to be just one term, and that is the constant term. It's possible for the highest order term to be simply x to the 0, in which case we have a0 x to the 0 or just a0, which is a constant. If we take a few examples of polynomial functions, they look something like this. Let's say p of x. Px, let's define it as x squared plus 2x plus 1. This is a polynomial function. Similarly, let's define another one. Qx is 3x to the 4th power plus 2x cubed plus 7x minus 2. This is also a polynomial. In fact, any polynomial, any function which has x to the n powers which are in positive integers and some constant coefficients in front of them is a polynomial. This function, which I'm writing just for the sake of explaining, something like x squared plus 1 over x, is not considered a polynomial function. We should not have negative powers of x. We should have non-negative or positive including 0 powers of x. Hence, n has to be an element of integers positive inclusive of 0. However, even though 1 over x containing functions like the one I've just drawn here are not polynomials, this is considered a polynomial. This is considered a polynomial. Similarly, let's say our s of x is equal to 2x plus 3 or just x plus 1. Let's say x plus 1. This is also a polynomial. These functions are considered to be polynomial functions. So, non-negative powers of x containing functions, and they need to be positive integers. Functions that are a set of positive integer powers of x with coefficients or constants in front of them is what constitutes a polynomial function. So any function of the form an x to the n, an minus 1 x to the n minus 1 all the way down to the constant a0 is a polynomial function. No negative powers of x, no other different functions like logarithms or sines or cosines or any of that. Just simply integer powers of x for positive integers n. So now that we've defined what a polynomial is, let's look at some special cases of polynomials. So going down, one special case is a linear function. Linear function. Linear function, as you might guess, describes a straight line. The function fx equals ax plus b, where a is not 0 and a and b are elements of the real numbers, is what we call a linear function. This function describes a straight line. If you plug different values of x and you plot fx versus x, you will get a straight line, indicating that this is a linear function. Note the stipulation that a is not 0, because when a is 0, this function is a slightly different form, which is a constant function, a flat line. So we want to exclude that case in this situation, which is why linear function contains the fact that a or the coefficient of x is not equal to 0. The next type of function which we are going to talk about is a quadratic function. quadratic, which you have dealt with in your O-level times. Quadratic function is a function fx equal to ax squared plus bx plus c, with the stipulation that a is not 0 and a, b and c are elements of the real numbers. So this is the stipulation for a quadratic equation or quadratic function. A should not be 0, because if a is 0 here, if this part is 0, then we are left with bx plus c, because a0 means the x squared part is not influencing at all, in which case we are just left with bx plus c, which is exactly equal to a linear function here. So to separate the linear functions from the quadratic functions, we give the extra condition that a should not be equal to 0. Similarly, the next one which we have a proper name for within the syllabus is the cubic function. Cubic function, which is the function of the form fx equals ax cubed plus bx squared plus cx plus d, with the condition that a is not 0 and a, b, c and d are elements of the real numbers. This is the only condition for a cubic function. Again, the fact that a is not 0 is to separate cubic functions from quadratic functions. In this case, if a is 0, this whole term becomes 0. So we are left with bx squared plus cx plus d, which is exactly equal to a quadratic function. So to separate the two, we add the condition that a should not be 0 in this case. So there are of course names for higher order functions than this. If you have a fourth power, x fourth power containing function, it has of course a name, but we are not discussing it within our syllabus. Similarly, a fifth order function has a name, which we are not discussing within our syllabus again. We are only discussing up to what a cubic function is, because, well, when you get to higher orders like fourth powers, it becomes very difficult to solve these equations. Well, not difficult, just more difficult than our syllabus is expecting us to be able to do. But of course, they exist and we can solve for them. So now I would like to introduce, before we continue, a couple of terms in our terminology. When we have polynomial function fx equal to ax to the an x to the n plus an minus 1 x to the n minus 1 dot dot dot, adding all of these to a1 x to the 1 plus a0, these symbols, these a's, a sub n minus 1 all the way down to a sub 1 and a sub 0 are what we call the coefficients. So here, coefficients, what we mean by coefficients are the an minus 1 comma all the way down to a1 and a0. These are the coefficients of the polynomial function fx. What we mean by the terms, if ever someone says the terms in a polynomial, the terms are the different components like an x to the n and an minus 1 x to the n minus 1 all the way down to a1 x to the 1 and a0. Each of these blocks that we're adding together is what we call a term of the polynomial fx. There's a couple others like the leading term. Leading term is highest, I misspelled that, highest x to the r term. So the term with the highest power of x. In this case, that would be this term right here, a sub n x to the n. It's the highest power x. So we could also write highest r. So the highest power x to the n with the highest n is the x to the n is the leading term. So in this case, a sub n x to the n is the leading term of the polynomial fx. Similarly, there's another word that we use which is called the order. The order of the polynomial is the largest r, is the actual highest r. So in this case, the order of this polynomial is n, because that's the highest power of x that we have here. Note the difference between these two. The leading term is the entire term itself, but the highest r is the order. So here this polynomial is of order n, but the leading term of the polynomial fx is a sub n x to the n. There's also another word we use, the leading coefficient. Leading coefficient, which it should be somewhat clear what this is. The leading coefficient is simply the coefficient of the leading term. So we could write coefficient of leading term. So in this case, that would be just a sub n. A sub n is the leading coefficient. The order is n. The leading term is a sub n x to the n. The terms are a sub n x to the n, a sub n minus 1 x to the n minus 1, so on all the way down. And the coefficients of these terms are a sub n minus 1, a sub n minus 2, all the way down to a sub 1 and a sub 0. These terms will be often used within this video and within other topics where polynomials are used. So it's important that you remember these and understand what they mean. Going back upward, if we just consider each of these cases, for the linear function, the order is 1 because we have a highest power of x to the 1. So the leading term is ax, the leading coefficient is a, and the terms are ax and b. So here this is order 1, the leading term is ax, the leading coefficient is a, and the terms are ax and b. And in terms of the coefficients are a and b. For the quadratic function here, the leading term is ax squared, the order is 2, the leading coefficient is a, the coefficients are a, b and c, and the terms are ax squared, bx and c. Similarly, if we go to the cubic, just as an example, I'm doing this just as an example so you better understand what each of these meanings of these words are. For the cubic function, the highest ordered term or the leading term is ax cubed, the order is 3, the leading coefficient is a, the coefficients are a, b, c and d, and the terms are ax cubed, bx squared, cx and d. So I hope that explanation gave you a better understanding of what each of these words mean. Coefficients, terms, leading term, order and leading coefficient. Now that we've established that, let's go on to something that's very important and very useful, specifically when you're finding an unknown polynomial or are trying to equate two polynomials and find what each of these constants are. So let's go to that. Suppose we have two polynomials px and qx. So suppose we have px and qx. And suppose I tell you that px and qx are identical. So we're saying if px and qx are identical. So what does this mean? This means that the polynomial function px is the exact same as the polynomial function qx. They are describing the same exact function. They will look the same if you plot them. If you put any input, you will get the same output. So what this means is that p of a, if you input a into p, it will be exactly equal to q of a for all a's in the real numbers. This is what this means. No matter what you input into here, p of a will be equal to p of b for every possible a in the, p of a will be equal to q of a for every possible a in the real numbers that we could input into here. So here this leads us to an interesting property of these two functions. If we write them down, I will explain to you what they mean. So let's suppose px is an x to the n plus an minus 1 x to the n minus 1 plus dot 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 all the way down to a1 x to the 1 and a0. And let's suppose also that qx is of a similar form. It's equal to b sub n x to the n plus b sub n minus 1 x to the n minus 1 plus dot 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 all the way down to b1 x to the 1 plus b0. Let's suppose these two are the expressions for the two polynomials. So given this, if PA is equal to QA for all A, then it should be the case that PX minus QX is equal to 0 for all X's element of the real numbers. This should also be the case. Given that if we write this down and we write these two instead of Px and Qx, let's group the x to the n and x to the n minus 1 terms. So what we get on the left hand side is that an x to the n minus bn x to the n. This term are going to group it. Plus, and then an minus 1 x to the n minus 1 minus b n minus 1 x to the n minus 1 grouped plus all of these all the way down to a1x minus b1x plus a0 minus b0. All of this has to be equal to 0 because that's our condition here. So now, factoring out these, we can see that an minus bn times x to the n plus an minus 1 minus bn minus 1 times x to the n minus 1 all the way down, adding all of these together, and then finally on this side a1 minus b1 x plus a0 minus b0 has to be equal to 0. So this has to be equal to 0, and it has to be equal to 0 for all x in the real numbers. Now note this condition. This has to be the case for every possible x in the real numbers. So given that, note that when x gets really big, each of these numbers gets really big. Let's consider the positive case. If x gets really big, goes to infinity, each of these numbers x to the n minus 1, x to the n minus 2, all the way down to x to the 1 will get really big. So given that all of these numbers get really big, the only way that the whole thing is still equal to 0 is if every single pair of these coefficients is equal to 0. So this is equal to 0, this part is equal to 0, this part is equal to 0, this part is equal to 0, all the way along is equal to 0. Because if any one of them is not equal to 0, then the one of them that has the highest power of n will be exploding to infinity as x goes to infinity, which should be the case because x is a real number. So as x goes to positive infinity, if even one of these pairs of coefficients is not equal to 0, then the value of the px minus qx would go to some infinity, either positive infinity or negative infinity, we don't know, but it will go to some infinity. The only way that is equal to 0 is if every single pair of these coefficients is equal to 0. So then, what does this give us? It gives us that an minus bn is equal to 0, meaning that an is equal to b sub n. Similarly, it also gives us that a sub n minus 1 is equal to b sub n minus 1. It gives us that a sub, I'll write a little bit more, a sub n minus 2 is equal to b sub n minus 2, all the way along until we get to a2 being equal to b2, a1 being equal to b1, and a0 being equal to b0. So what have we found? We've found that if two polynomials px and qx are identical, then every coefficient corresponding to equal powers of n, or let's say r for now because we want a counting number, every possible x to the r power coefficients of the first polynomial and the second polynomial have to be equal. A sub n is equal to b sub n, a sub n minus 1 is equal to b sub n minus 1. This becomes useful when we want to find functions that we don't know using functions that we know. For example, if we know px, we know px is, let's say, something, we know qx is something. Let's say px is a x to the 4th power plus 3x cubed plus x minus 6, and we know that qx is 3x 4th plus bx cubed plus cx squared plus x plus d, let's say. If we know this, and we know that px is exactly the same as or identical to qx, then we can say, comparing the x powers of each of these polynomials, the coefficients of the fourth power of x need to be equal. The coefficients of the third powers of x need to be equal. The coefficient of the second powers of x, which in this case is non-existent, and here this need to be equal. The coefficients of the first powers of x need to be equal, and the coefficient of the zero powers of x need to be equal. So that means that for the fourth powers, a and 3 need to be equal. So a equals 3. And the third power's coefficients need to be equal. So 3 and b need to be equal. So 3 equal to b. The coefficients of the second powers need to be equal. In this case, there's no second power, which means that we have actually 0 times x squared happening here, which we have not written, but it's there, it exists. So we have 0 times x squared here, we have c times x squared here. So therefore c and 0 need to be equal. So c is equal to 0. And finally, here x to the 1 powers are there, but both of them are already equal, so we don't have to do anything here. We know both of them are equal to coefficient of 1. And finally, for x to the 0 powers here, we have x to the 0 here, x to the 0 here. So therefore, negative 6 and positive d have to be equal. So d is equal to negative 6. And there we go. We have found the constants a, b, c and d simply by the fact that we know that p of x is equal to q of x. They are identical to each other. Now note that all of our actual practical examples of this being used will not be this simple. There will be some messed up function on the right side or the left side, or some possibly partial fractions is one case where we use the x to the n powers. Another case is when we have some remainder and some factor and we want to equate the two or something like that. But for now, just understand and maybe try some exercises to see if you can properly do this. Understand the fact that the coefficients of any x to the r power in two polynomials should be equal if the two polynomials are identical to each other. If the two polynomials are identical to each other, not equal to each other. This triple equal symbol, or the fact that both polynomials give the same output at every possible value of their inputs, should be the case. It's not that p of a equal to q of a. This is not sufficient. It needs to be p of a equal to q of a for all a in the real numbers. This condition is important for us to do this coefficient matching. Otherwise, what we have instead is simply one solution for the two equations being equal to each other. If they are identical to each other, only then can we compare coefficients. So remember that. Do not compare coefficients when you're trying to solve an equation. Compare coefficients when you know that two polynomials are identical, not equal. There's a difference between equal and identical. So I'm stressing this. I think I've spent about 2 minutes talking about this because it is very important to understand the difference between identical and equal. So now that we understand how to compare two polynomials and use that to find unknown coefficients or some other use case that we can find, let's now move on to a different thing, which is doing algebra with polynomials. And in fact, put a subheading here: algebra with polynomials. So similar to how we can do algebra with numbers, we can add numbers, subtract numbers, multiply and divide numbers, we can perform algebraic operations on polynomials as well. We can add two polynomials together, we can multiply two polynomials together, we can even divide one polynomial by another, which we will get to. So just understand that these are possible operations, and we have to kind of go back to a little bit of the basics to understand what's actually happening here. So let's get into it. Suppose that px is an x to the n plus an minus 1 x to the n minus 1, this whole thing all the way down to a1 x to the 1 plus a0. And suppose that qx is the whole thing again. I'm going to speed up this part probably. So now that we have this, suppose these are the two functions. Let's define another function which I'll call a of x and say that this function is equal to p of x plus q of x. And let's get a notion for what this means. This means that whatever a of x is, it is the same as taking p of x and adding q of x to it. So for all x, this is true. For all x in the real numbers, this first condition is true. If this is the case, then this means that a of x is equal to this thing plus this thing. So if we write that down, a of x is equal to, and I'm going to do some pairing here. I'm going to pair the x to the n terms, x to the n minus 1 terms, all of these terms I'm going to pair and write it like we did earlier. So this would be a n x to the n plus b n x to the n plus a n minus 1 x to the n minus 1 plus b n minus 1 x to the n minus 1 dot 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 all the way down up to a1x plus b1x plus a0 plus b0. So now considering this, all of these are equal, let's now factor out all of the x to the r terms out and see what we get. We get that ax is equal to an plus bn times x to the n plus an minus 1 plus bn minus 1 x to the n minus 1 plus dot 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 all the way down to a1 plus b1 x to the 1 plus a0 plus b0. So what happened here? When we added these two polynomials together, every corresponding pair of coefficients with the same order, the same x to the n power, were added together. So simply, when we are adding two polynomials together, all we have to do is write every x to the r power with its coefficient in the first polynomial plus its coefficient in the second polynomial added together and put in the front. That's all that this is. Addition of polynomials is quite straightforward. Similarly, I won't go into subtraction of polynomials in the same detail, but I'm going to quickly write down what that is. If bx is px minus qx for all x in the real numbers, then what this means is that bx is equal to an minus bn x to the n plus an minus 1 minus bn minus 1 x to the n minus 1 dot 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 all the way down to a1 minus b1 x to the 1 plus a0 minus b0. So same exact thing. You could even think of addition as negative, actually subtraction as negative addition in order to derive this second formula. So these two are quite straightforward. It means that all you have to do to add two polynomials together is simply match up the coefficients of the corresponding x to the r powers and add them together. If we quickly do some examples of this, suppose that fx equals 3x to the 4th plus x squared plus 2x plus 1, and suppose that gx is equal to let's say negative 4x cubed plus 4x squared minus 2. In this case, fx plus gx, if we consider fx plus gx, this is simply considering the x to the 4th powers. The first one has a coefficient of 3, the second one has a coefficient of 0, because notice there's no actual x to the 4th power here, which means it has a coefficient of 0. So then we have 3 plus 0 x to the 4th, which is 3x to the 4th, plus here we have no x cubed term, because notice again the coefficient of the x cubed term in fx is 0, but the coefficient of the x cubed term in gx is negative 4. So actually I prematurely put a plus there. It's actually supposed to be minus 4x cubed. Now as for the x squared terms, in fx there's a coefficient of 1, in gx there's a coefficient of 4, adding the two together there's a coefficient of 5x squared happening here. In fx there's a coefficient of 2 for x to the 1. In gx there's actually no x to the 1 coefficient, which means it's 0. So we have 2 plus 0, which is 2x. And then in terms of x to the 0, fx has a coefficient of 1, gx has a coefficient of negative 2. Adding the two together, we get negative 1. So fx plus gx is this, and I'll leave it as an exercise to you to find fx minus gx and write it down. I'll also leave it as an exercise to you to find gx minus fx and write it down. So as an exercise left to you, go ahead and do these two and come back to the video. Alright, so now we know how to do simple addition and subtraction with polynomials. Let's now tackle how we do division and multiplication. We'll do multiplication first because it's more straightforward. Say that we have two polynomials. We'll use the same ones earlier, so I'll actually go up here. I'll copy these two definitions. We're not going to go through it we're not going to go through it term for term, but we're going to use it as a reference to try to understand what's happening here. So given that px is this and qx is the second one, let's now consider what we mean by px times qx. So px multiplied by qx would mean we take all of the values in px and put a bracket around them and multiply that by all the values in qx. So we have one sum multiplied by another sum. We have all the sums of a sub n next to the n's and all of those, and all the sums of b sub n next to the n's and all of those multiplied together. In this case, I'm actually going to change this symbol here. Instead of n, I'm going to put m, because there's another point which I want to mention here. So in this case, we have now qx has b sub m x to the m and all of those powers. Again, m has the same restrictions that n had earlier. M is some positive integer, similarly as n is some positive integer, and everything else has the same exact meaning. So when we multiply px and qx, we have essentially to multiply all of this added together by all of this added together. So by the distributive and commutative properties, we can see that what we have to do is multiply each term in the first sum by the entire second sum and then expand that second sum as well. So we can say this is the same as doing a sub n x to the n times the entire sum of qx plus a sub n minus 1 x to the n minus 1 times the entire sum of qx plus, and you can see where this is going, all the way down to a 1 x to the 1 times the entire sum of qx plus a0 x to 0, I'm not going to write, times the entire sum of qx. This is essentially what we have to do in this situation. We have to compute all of this, and then qx itself is also another sum. So we can distribute this multiplied number across the entire sum. And what we get then is a sub n x to the n times every single term in qx. So I'll write the first one for now. First one is b sub m x to the m, and then we have a n x to the n times the next term, which is b sub m minus 1 x to the m minus 1. We have a bunch of these until we end with all of the terms from the first one. So if I'll actually write that, plus a sub n x to the n times b1 x to the 1 plus a sub n x to the we are ending at n and times b sub 0. All of this entire set of terms here came only from this part. So this part produced all of these terms. Similar to this, there will be another sum coming from the second term. There will be another sum coming from the third term all the way down until the very last term. So what we have is a sum of products. A bunch of different products all summed together. So here, every single possible combination of a to the a sub r x to the r's and b sub k x to the k's is happening here. We have every single possible sum. If I write out a bunch of all these sums and then the very last sum will be a sub 0 times qx. I'm going to write only that down because if I wrote all the others it would drive me mad, it would drive you mad. So we're going to leave it and just consider the very last sum. Now every single sum in the middle is the exact same format. Just multiply a sub n x to the n minus 1, a sub n minus 1 x to the n minus 1 by every single term in qx. Do the same for the next one and the next one and the next one all the way down to here and here. The very last term of this sum will be a sub 0 times b sub m x to the m plus a sub 0 b sub m minus 1 x to the m minus 1 all the way down up to a sub 0 b sub 1 x to the 1 plus a sub 0 b sub 0. So note, the final term produced here has no x power. It is simply x to the 0. And the very first term produced here is a sub n x to the n times b sub m x to the m. Now consider what the powers of this thing are. Here, n is the highest power or the order of px. M is the highest power or the order of qx. So here we have x to the order of px times x to the order of qx. If I simplify this using our known algebraic laws, we can get that this is equal to a sub n times b sub n times x to the power of n times x to the power of m is equal to x to the power of n plus m. So we have a bunch of other terms, of course, which I'm going to ignore, large number of terms in the middle, and finally a sub 0 b sub 0. So we have every single power of term in the middle here. Some of their coefficients may be 0, which we will ignore for now, and we'll just write them down. But the highest power term is x to the n plus m, and the lowest power term is the constant term here. So what does this tell us? This tells us that if px is of order n and qx is of order m, then multiplying px by qx will result in some polynomial here, some polynomial. This is also still a polynomial, recall. Every single power which are integer powers, positive integer powers, are there in the middle here, which so meaning this is also a polynomial. And in this polynomial we have a highest order term or an order of n plus m. So we can see that if px is order n, I'll actually write that down as a theorem. If px is order n, comma qx is order m, px multiplied by qx is a polynomial of order n plus m. The highest power is now n plus m. We can write that as a theorem and conclude that that is all we have to talk about multiplying two polynomials together. We'll now do some examples so that you can really ground yourself with this concept, and I'll also show you how that property of the orders getting added up is clearly shown. So let's consider the two polynomials. Let's say fx equal to x squared plus 2x minus 1 and gx is equal to 2x plus 3. Both of these are polynomials. I'm writing simpler polynomials here because it will make the multiplication simpler. Otherwise, we will have to do a lot of multiplication, a lot of effort to find fx times gx. So now let's consider fx times gx, and consider what that's equal to. This is the same as writing 2x plus 3 times x squared plus 2x minus 1. So here, by distribution, we can see this is also equal to 2x times x squared plus 2x minus 1. You don't have to do it like this, of course. You can do it in the head if you can. I'm just showing you exactly how it happens. Distributing this thing, we can see this is 2x times the second product plus 3 times the second product of x squared plus 2x minus 1. So now distributing the 2x among the first product, we can see that this is, so for first sum, we can see that 2x times x squared is 2x cubed plus 2x times 2x is 4x squared plus, and then 2x times negative 1 is negative 2x. So I'm actually going to cut that plus and write negative 2x. So that's the first bracket solved, plus 3 times the second bracket. So 3 times x squared is 3x squared, plus 3 times 2x is going to be 6x, and 3 times negative 1 is going to be negative 3. So we have this. Now we can expand these brackets, remove the brackets, and add the terms which have the same powers of x. By doing that, we can see the first one by our simple addition formula for polynomials which we found earlier. The first one has a x cubed term, the second one has x cubed term of coefficient 0. So therefore the x cubed term in the final answer will be 2x cubed plus. In terms of x squared, the first one has a coefficient of 4, the second one has a coefficient of 3. So the overall will have a coefficient of 7x squared. In terms of x to the 1, this has a coefficient of minus 2, this has a coefficient of 6. Adding the two together will give you plus 4x. In terms of constants, this has no constant or 0 constant. This one has negative 3 constant. So negative 3 carries down. So therefore fx times gx is 2x cubed plus 7x squared plus 4x minus 3. Now consider the order here. Fx was order 2. Order 2. Recall, because here the highest order term has a coefficient as a power of x squared. Gx was order 1, because the highest power here has a power of 1. So it's order 1. What's the order of fx times gx now? Well, looking at fx times gx, we can see the highest power is of this one, x cubed. So then the highest order is x cubed in this case, which means we have an order of 3. Now consider 2 plus 1. As we all know, 2 plus 1 is equal to 3. So our formula here, our theorem that px being order n and qx being order n will produce px times qx as a polynomial of order n plus m is correct here. We have an order of n plus m happening here. So there, we have proven that if fx, or let's say px is order n and qx is order m, then the product of the two will be of order n plus m. Now let's take some time and consider what division means with polynomials. Now I should warn you, unlike the others we discussed above, division needs us to go back a little bit to the basics of division and understand what division really means. Because for polynomials, division does not mean that we get a decimal number or some fraction or some continuous infinite decimal or something like that. In fact, with polynomial division, we get remainders in our division. So it's like we're back in the 5th grade times, right? Remember the scholarship examination? Back in those days when you're doing division, we always had remainders. We never factored all the way down and divided until we got an infinite decimal. So we're actually in polynomials having remainders, and now let's take a look at how we divide one polynomial by another polynomial. Alright, so now let's try to figure out how we do polynomial division. So in order to do this, we need to go back to a little bit of basics. Because the two polynomials we are dividing would be composite functions, it's not too easy for us to simply divide the top by the bottom and write some decimal expansion. That doesn't work. It works for numbers, it doesn't work for polynomials. Instead, we have to go back to a method of division with remainders. If you will recall your 5th grade, which I hope you do, if you are 5th grade learning, doing something like 17 divided by 5 in 5th grade looked like this. Does 17 contain 5s? 17 does contain a 5. It contains one 5. It is 12 plus 5 divided by 5. I can take that 5 out and write 1 plus 12 divided by 5. Does 12 contain any more 5s? It does. It contains another 5. So I can write this is 1 plus 7 plus 5 divided by 5. Now I can remove that out and say that this is 2 plus 7 divided by 5. Does 7 contain any more 5s? Well, yes, it does. 7 contains one more 5 and I can write that as 2 plus 5 divided by 5. Now I can take this 5 out and I have 3 plus 2 divided by 5. Does 2 contain any more 5s? No, it does not. I cannot remove any more 2's from 5, 5's from 2, which means that we are done here. So that means 17 divided by 5 is 3 with remainder of 2. We did not know how to divide 2 by 5, so we just left it as a remainder of 2. This exact method is what we are going to need to divide one polynomial by another polynomial, because we do not know how to exactly divide one thing by another. For example, we cannot easily divide x plus 1 divided by x squared minus 2x plus 2, let's say. We cannot easily divide the top by the bottom. It is not easily possible. We do not even know how to start. So instead, what we do, we just leave it as a remainder. Anything that we cannot divide, we leave as a remainder. Anything that we can divide, we divide it and take it out. So what do I mean by divide? Well, divide is the opposite operation of multiplying. So what I mean is, when I say let's divide polynomial px by polynomial qx, is that let's find whatever number we could have multiplied by qx, whatever polynomial we could have multiplied by qx to get px. So we can do this with normal numbers to get a better understanding. Let's say 16 divided by 7, let's say. So for 16 divided by 7, what we can think of this as is, we can think of this in a different way and say 7 times question mark plus another question mark is equal to 16. What is this and what is this? In this case, we can keep increasing this first question mark until we go too high. If we put a 2 here, we get 14, it's alright. But if we put a 3 here, we get 21, which is higher than what we started with, which is 16, so it's not going to work. So that means this first question mark must be 2. So we have 7 times 2 plus question mark is equal to 16, meaning 14 plus question mark is equal to 16, meaning the question mark is 2. So this is how we do the idea of division without actually doing division. Instead of doing division, we just think what could we multiply the first thing by to get the second thing. So we use this to conceptualize dividing polynomials. Let's say we want to figure out what px divided by qx is. Qx is what? And here we have a stipulation that qx, this thing is not equal to 0. Because if qx is equal to 0, we are dividing by 0. We really don't want to do that. So qx is not equal to 0. That's important. So considering px divided by qx, if I consider that that is equal to something, that means that px is equal to qx times something, which I'll call rx, plus some leftover, which I'll call sx. This is the exact same format as finding 16 divided by 7 in terms of 7 times something, some unknown, plus some other unknown. This unknown is our quotient, this unknown is our remainder. So in this case, px is the numerator, this right here is what we call the numerator. Qx is what we call the denominator, what we are dividing by, denominator. Rx has a special name, it's called the quotient, and Sx has a special name, it's called the remainder. So essentially what we mean by what is px divided by qx is what are the two functions rx and sx, the two polynomial functions rx and sx, such that multiplying qx by rx and then adding sx gives us px. This is exactly what we mean. So let's try and figure out the algorithm for actually doing this operation. So let's take some examples. Let's say that fx is equal to 2x squared plus 7x minus 9, and that gx is equal to x plus 3. Let's just say this is the case. If we want to find fx divided by gx, what we essentially want is what are the two functions rx, the polynomial functions rx and sx, such that fx is equal to gx times rx plus sx. So what we have here, what we mean by this thing, fx divided by gx, is what are the two functions such that fx times, or fx we'll write as 2x squared plus 7x minus 9 is equal to x plus 3 times some r of x which we want to find plus some s of x which we also want to find. What are these two functions? So considering this and taking 2x squared plus 7x minus 9 divided by x plus 3. We know that a remainder does not contain any of the denominator in it. For example, when I divided 16 divided by 7, the remainder I got was the smallest number possible and the number such that there were no 7s in it. This number here was chosen so that it was small as possible by making this first number big as possible, such that there was still none of the denominator within that number. When dividing polynomials, we do the same exact thing. We try to make sx as small as possible by making rx as big as possible. So in this case, first, there are no apparent gx's or no apparent denominators found within the numerator. So what we are going to do is try to create some. So by doing that, first, for the highest order term, if we consider, we have 2x squared. If we consider some polynomial multiplied by x plus 3 equaling 2x squared, we can see that 2x times x plus 3 would give us a 2x squared. It would give us 2x squared and it would also give us another 6x. So if we can find a 2x squared plus 6x in the numerator, then we can divide that part out as a 2x. We can take this 2x to be part of the quotient. So doing that, if we take this thing here, we can see we can divide out a 2x squared plus 6x, which would mean we are left with another extra x, another x here, and a minus 9, and the whole thing needs to be divided by x plus 3. So taking this part only, we can factor out an x plus 3 here. We can factor this out as 2x times x plus 3 divided by x plus 3 plus another extra x minus 9 divided by x plus 3. So this part can be easily divided and that will give us 2x here, and we still have a leftover x minus 9 divided by x plus 3. Now we again ask the question, because we want the largest rx possible, we ask, can we add anything more to rx? And considering this thing, we have to ask the question, are there any more gx's present in this above formula here, this above polynomial? And it turns out there are. Consider x plus 3 times 1. This is just x plus 3. We could potentially find an x plus 3 up here by simply manipulating the variables to produce an x plus 3. What I mean by this is, say in the numerator, let's say 2x plus, instead of x minus 9, if I do x plus 3 and then subtract the extra 3 that I added and then do the minus 9, so here I have added a 3 and removed a 3, which is essentially the same thing as doing nothing, so there's no issue here. But if I add a 3 and remove a 3, now I can see that I can factor this part and divide by x plus 3. This part can be taken out, this x plus 3 can be taken out as a 2x, and here this x plus 3 can be taken out as a plus 1, and we are left over with minus 3 minus 9, which is minus 12 divided by x plus 3. Now once again, because we are looking for the largest rx, we have to once again check and see if there are any more x plus 3s that can be removed from this numerator here. So in this case, negative 12. There are no x's, meaning there is no number that we can multiply x plus 3 by. There's no polynomial and there's no number even. There's no constant that we can multiply x plus 3 by to give us negative 12. It is simply impossible. Because of that, we can see there's no more x plus 3s or denominators that we can take out of this numerator here. So that must mean that this is our remainder. This is the same exact thing that we did for normal numbers. when we did over here 17 divided by 5, we kept removing 5s until we got a number on top that it seemed we could not remove any more 5s from. In the same way, as we divided this polynomial, we found some value, some polynomial on the top, of which it appeared that there were no parts of the denominator that we could remove. There are no x plus 3's in the numerator that we could simply remove out. That must mean that this is the remainder. So then, we have a part of 2x plus 1 which we have removed successfully by factoring out x plus 3's, and we were left with a minus 12 that we could not factor out using x plus 3's. So that must mean that this is our quotient and this is our remainder. In fact, if we write down fx was 2x squared plus 7x minus 9, 2x squared plus 7x minus 9, this is in fact equal to g of x, which is x plus 3. X plus 3 times the quotient we found, which is 2x plus 1, plus the remainder that we have, which I'm going to write as a plus, and negative 12. So here we have found our values. This was the numerator. This was our denominator. This was our quotient, and this was our remainder. So there we have successfully found the quotient and the remainder using this method. So what we did was repeatedly target the highest order term and try to factor out an x plus 3. At times, in order to do this, I want you to note this, at times in order to do this we had to add and remove the same thing. Notice here we had to add and remove the same thing. This is a very common occurrence when you divide one polynomial by another. You will at times need to add something and remove that same exact thing. In this case we added and subtracted 3 here. If you have more complex polynomials or as your numerator and denominator, you will have to add and remove more complicated things. So if we analyze what we did, we started out with a polynomial of order 2 on the top. We divided it by a polynomial of order 1 on the bottom. And in the end, we got a polynomial as the quotient of order 1 and a remainder of order 0. So here there's actually a relationship here, and there's another interesting thing which we need to cover. We need to also cover the case where the order of the numerator is equal to the order of the denominator and the order of the numerator is less than the order of the denominator. In this case, we were able to successfully divide the top by the bottom because the order of the top was greater than the order of the bottom. This is a necessity. So I'm actually going to label this as case 1. So this is case number 1. Case number 1 is order of numerator is greater than order of denominator. So right now I'm going to spoil something for you. In this case, if the order of the numerator, let's say order of numerator is called n and the order of the denominator is called m, it is the case that when we do this, the quotient will have order n minus m. Provided that n is greater than m, the quotient will have order n minus m, and the remainder will have order less than m. Actually, I've written this the other way, less than m. The order of the quotient of the remainder will be less than m, and the order of the quotient will be n minus m. Now this is the proof of this is kind of similar to the proof where we multiplied two polynomials together and found that the order of their product is equal to n plus m. This is of course a similar level of proof difficulty which I'm not going to actually do within this video. I'm not going to prove that the quotient is order n minus m when n is greater than m. I'm just going to give it to you. So I'm going to give to you that if we divide order n polynomial by order m polynomial, this will give us a quotient of order n minus m and remainder of order which is less than m. This is the case, and I will not prove this but just give it to you as given. If you want, you can try to prove that it's true also. In fact, all you have to do is use this identity saying that dividing fx by gx, or here dividing px by qx, is equivalent to finding the polynomials rx and sx such that qx times rx plus sx is equal to px. In fact, here you can see, I'll quickly do it. If this is order n and this is order m, then these two orders are adding together. We can see that this thing's order has to be less than these guys' order, because otherwise we would have the case that there were more denominators that we could have removed from the remainder. This cannot be the case, no? Similarly, when we are dividing numbers, we cannot have a remainder which is greater than the denominator. In the same way, the order of the remainder cannot be greater than the denominator. So therefore, the order of the remainder has to be less than m. That part is clearly proven, less than m. And now, because the total order needs to be n, and we are multiplying two polynomials together, if this one has polynomial order of, let's say, k, it is the case that m plus k, because we are multiplying these together, recall we are multiplying these together, m plus k is equal to n, which means that k is equal to n minus m. This is of course not the rigorous proof, but this is good enough for you. The order of the quotient will be n minus m, as we can see clearly from this demonstration. So that was case number 1. The case number 1 is the case where the order of the numerator is greater than the order of the denominator, in which case there's no problems. Our remainder will have order less than m, and our quotient will have order n minus m. In the case 2, where n is equal to m, i.e. we have px divided by qx, where the px has order n, qx has order m, but n is equal to m. In this situation, we get something interesting. We get that we can divide the top by the bottom and we get a quotient. According to the above one, the quotient's order will be n minus m. What this means when the two functions are of same order is that the quotient will be order 0. In this case, quotient is order 0. The quotient in this case will be order 0, and similarly the remainder will be of order less than m, or we can even write less than n, because m and n are the same thing. This is not really all that special of a case, as in it's not different from the first case. In fact, I could have written that this is the case for n greater than or equal to m. However, here we are getting a little something special. When n is equal to m, we are getting a quotient of order 0, which is just a number, which is why I decided we are going to separate it as a separate case. So this will be something like, let's give an example, 3x squared plus 2x minus 1 divided by x squared minus 4x plus 3. So let's try to divide this thing. If we try to divide this, first we need to try to find a group of x squared minus 4x plus 3 in the numerator. So we can see, if we multiply the denominator by 3, we can get one of those. So here if we do 3 times x squared minus 4x plus 3, this will be 3x squared. So we are eliminating the highest order term here. We are eliminating the 3x squared, but we have an extra negative 12x plus 9. So we need to somehow get a negative 12x on the numerator, and we also need to get a plus 9 on the numerator. We can do this, of course, no problem. So to get a minus 12x on the numerator, what we are going to do is do 3x squared minus 12x, and to get a plus 9 on the numerator, we're going to do plus 9, but then we're immediately going to undo that by doing a plus 12x and a minus 9, and this is going to remain as that, and then we're going to add the rest of it, which is plus 2x and minus 1, divide by x squared minus 4x plus 3. So now taking this thing, we have a 3x squared minus 12x plus 9 component, and in extra we have a 12x and 2x, which will give us 14x, and a minus 9 and a minus 1, which will give us minus 10. The whole thing divided by x squared minus 4x plus 3. So in this case, this part factors out as 3 times the denominator. So we can directly factor that out as 3 times the denominator, so we can remove it, plus another 14x minus 10 divided by x squared minus 4x plus 3. But now we run into the issue where the order of the numerator is less than the order of the denominator, meaning there's no more x squared minus 4x plus 3's which we could possibly pull out of the numerator here. So here we can see clearly the order of the quotient is 0 in this case, and the order of the remainder is less than the order of the numerator, or you could say less than the order of the denominator also. It's also still true. So that's the special case that we've drawn here. The quotient is order 0 and the remainder is less than n, where n is the order of the numerator and the denominator provided they are equal. In the equal case, the quotient is order 0, meaning if we have px divided by qx and px and qx are of the same order, then the quotient is a constant. That's what we can say. So now that we have established that, let's move on to case number 3. Case number 3, we really cannot do all that much in case number 3, but I'll show you what it is. In case number 3, we have that n is less than m, where n is the order of px and m is the order of qx. So in this case, we already do not have any qx's that we can potentially remove from p. Why not? Well, an example of this kind of situation where n less than m would be something like x minus 3 divided by x squared plus 2x plus 7. In this case, we already do not have even a single x squared plus 2x plus 7 that we could possibly remove from the numerator, which means that the quotient would have to be 0, because there's no polynomial other than the 0 polynomial that we can multiply by in order to get x minus 3. So that means that writing this equation in the multiplication form with remainders would give us x minus 3 is equal to some x squared plus 2x plus 7 times our rx plus sx. In this case, we can clearly see, this is of course the same as our earlier format of quotient and remainder. In this case, we can clearly see rx would have to be 0, because if rx is not 0, that means there's at least an x squared term on the right side, but there's no x squared terms on the left side. So therefore, rx, or the quotient, in this case is 0. So the quotient in this case is 0, not 0 order. Recall, over here, quotient is order 0 is what we had, don't confuse it. When n was equal to m, the quotient was order 0, but in this case, when n is less than m, the quotient is literally 0. Now if the quotient is 0, that means this part is 0. If this part is 0, that means this whole thing is 0. This whole thing is 0. So if this whole thing is 0, we have the thing on the top is equal to 0 plus the remainder. So therefore, what's the remainder? Remainder is equal to the original function, which is, I'm going to write as px. So in this case, the case where order of n is less than order of m, there is absolutely nothing we can do. We just have to write the remainder as the original function on top and the quotient as 0. So note this and these 3 cases. In the first case, we had n greater than m, in which case we could remove certain amount of the numerator from the numerator in chunks of the denominator, which would mean we get some quotient the quotient would have order n minus m, where n is the numerator's order and m is the denominator's order, and we would be left with some remainder which would have order less than the thing that we were dividing by. So that is the case. In the other case where n was equal to m, meaning the numerator and denominator were of the same order, we had a quotient which was of order 0, meaning it's a constant, and some remainder which was of order less than n. I should actually, instead of just writing remainder less than n, remainder order which is less than n. In fact, I'll erase the whole thing and write it nicely. Remainder whose order is less than n. Yes, alright, so that's consistent with the above. The remainder's order was less than n in the case where n was equal to m. However, if n was less than m, meaning the numerator has a lower order than the denominator, it automatically means that there's no polynomial we can multiply the denominator by in order to get the numerator. So then the denominator's product, by which I mean the quotient, must be equal to 0, because there's no other polynomial that we can put there in order to multiply the denominator by in order to give the numerator. There is no polynomial we can multiply x squared plus 2x plus 7 by in order to give x minus 3, or at least an order 1 polynomial. So that's it, the quotient is 0. Now given that the quotient is 0, this whole term becomes 0, which means that the remainder is equal to our original numerator. So we have that also. These are the three cases when you divide one function by another function. We will be going over some special cases of this in a little bit, but for now I would encourage you to pause the video here, write out some functions px and qx, and try dividing px by qx by yourself. See if you can understand how to do the polynomial division and come back to this video. I'll wait for as long as you take. Hello and welcome back. I hope you actually did some work rather than just waiting for me to skip to the next lesson. But now let's go. Now that we're in the next lesson, what we're going to cover now is something called the remainder theorem and the factor theorem. The factor theorem. So these two theorems are related to what we just did, dividing one polynomial by another, except there's a special case that we're doing. We're considering dividing a polynomial by x minus some number. So if we consider dividing fx, which is a polynomial, by x minus a, what this means is we're trying to find fx equal to x minus a times some function which I'm going to call qx plus some function which I'm going to call rx. Here qx is the quotient, and rx is the remainder. So we have this. We have that fx is equal to x minus a times qx for some qx plus rx for some rx. We do not know what the polynomials qx and rx are. That is what we are expected to find. So now, in this case, let's consider what happens when x is equal to a. Let's consider, just hypothetically think what happens when x is equal to a. On the left side, this division equation gives us that f of a, because now x is equal to a, recall. So we have f of a is equal to, in brackets here, times q of a plus r of a. So what's in the brackets? Well, replacing x by a, we have a minus a. Replacing this x with an a, we have a minus a. But a minus a is equal to 0. So this whole thing is equal to 0, which then means that f of a is equal to 0 plus r of a. So f of a is equal to r of a. So what does this mean? This means that if you divide fx by x minus a, then the remainder will be such that f of a is equal to r of a. whatever the remainder is, f of a is equal to r of a. Let's do a practical example of this and see what we're talking about. Let's consider x squared plus 2x plus 3 divided by x minus 1. So to do this, what we do, we just take as many x minus 1s out as we can. In this case, I can see I need to get rid of an x squared somehow. So to get rid of an x squared with x minus 1s, we have to multiply x minus 1 by x. Meaning, we need a x squared minus x term. So we can do that easily. We can do an x squared minus an x. But then we have to add another x to compensate. We have another 2x and another 3. Divide by x minus 1. In this case, this x squared minus x factors out an x minus 1, which means we get x times x minus 1, plus here we have 3x plus 3, divide by x minus 1. This will give us an x on the outside, plus another 3x plus 3. Now, to get rid of this 3x plus 3, we need to get rid of this 3x. We have an x. So we have to multiply the x by 3, which means we have to multiply the whole thing by 3 in order to get rid of this 3x plus 3. And what we need here is a 3x minus 3. So we can do that simply by doing 3x minus 3 plus 3 plus another 3. This thing is our two things that we added and subtracted again. And we do this thing, divide by x minus 1. So now here we have this 3x minus 3, which when we factor out the x minus 1, we get a 3x minus 1. And then this plus 3 and plus 3 give us plus 6, divide by x minus 1. So in this case, dividing the x minus 1 here, we get x plus 3 plus 6 divided by x minus 1. Now here, this is our remainder and this is our quotient. So we have quotient of x plus 3 and a remainder of 6, which means that our original function fx, or x squared plus 2x plus 3, x squared plus 2x plus 3 is equal to our thing we divide by, which is x minus 1, times our quotient, which is x plus 3, plus our remainder, which is 6. So in this case, if we substitute this root, here we divide by x minus a here, right? Here we divide by x minus a. In this case, we are dividing by x minus 1. So what we need to consider here is the case when x is equal to 1. Because here what we considered was the case when x was equal to a. So, substituting x is equal to 1 here, we can see that this part goes to 0. Because here, substituting x equals 1 here, we have 1 minus 1, which is 0. So, the whole thing goes to 0. On the left side, we have 1 squared plus 2 times 1 plus 3, which is equal to 6. And on the right side, we have 6. So, what do you know? The left side and the right side are equal, aren't they? Isn't that interesting? Yeah, well, this is to be expected, of course. We derived it. We literally wrote down what it means to divide a polynomial by another polynomial, and we showed that this is the case. So, this right here is true. This is what we call the remainder theorem. The remainder theorem is the fact that if the remainder, when fx is divided by x minus a is r of x, then we can say that f of a is equal to r of a. This thing here, this statement, which we have proven to be true, is what we call the remainder theorem. Remainder theorem. Now there's a special version of the remainder theorem which we call the factor theorem. Let's now work through what that is. So, what does it mean for a number to be a factor of another number? It means that you can perfectly divide. For example, I can say that 5 is a factor of 15. Now what this means is that 15 divided by 5 is 3 with a remainder of 0. If one number divided by another number has remainder 0, it means that that number was a factor of the other number. If a divided by b has remained 0, then b is a factor of a. This applies to polynomials as well. And you can probably see where it's going when I said that remainder equals 0. If we have the case where fx and gx are the two functions which we are considering, and fx divided by gx gives us something such that fx is equal to gx times quotient of x plus a remainder of x, where the remainder of x is equal to 0, i.e. there is no remainder. Gx times qx is a perfect multiple to give you fx. Then it follows that qx and gx are both factors of fx. So then gx was a factor of fx. Now considering this, if we have fx divided by x minus a again, and this is a factor, x minus a is a factor, what this means is that fx is equal to x minus a times some qx. So again let's consider case when x is equal to a. When x is equal to a, in this particular case, we have on the left side f of a, because x is equal to a. On the right side we have in the brackets a minus a times q of a. Sorry, not g of a, q of a. So in this case, a minus a is 0, which means this thing is 0, which means this whole thing is 0. So on the right side we have 0 is equal to 0. What this means is that f of a is equal to 0. So what this means is, if we ever have f of a being equal to 0, we can say that x minus a is a factor of fx. Or if we know that x minus a is a factor of fx, we can say that f of a is equal to 0. These two are what we know as the factor theorem and the converse of the factor theorem. The factor theorem states, if x minus a is a factor of fx, i.e. fx is x minus a times qx for some qx, some polynomial function qx, then we can directly say that f of a is equal to 0. This right here is the factor theorem. This is the factor theorem, and there's also a converse of the factor theorem. The converse of the factor theorem is going in the reverse direction. Here we are starting with x minus a being a factor of fx and deriving that f of a has to be equal to 0. The converse of the factor theorem is the one that's such that, considering this, if fa equals 0 for a polynomial fx, then x minus a is a factor of fx. These two are the inverse of each other. First one, x minus a was a factor of fx, leading to fa being 0. Secondly, if fa is 0, then x minus a is a factor of fx. So these two are essentially the same theorem, but going in reverse directions. This is the converse of the factor theorem. We actually have a way to write this. From the first thing, what we get is that x minus a being a factor of fx implies that fa is 0. From the second one, what we get is that fa being 0 implies that x minus a is a factor of fx. So we can write this. You might not know this, but in logic, if a implies b, given that statement A implies statement B and statement B implies statement A, we can write this in a special form saying that A happens if and only if B happens. This kind of double arrow. The meaning of this double arrow is that the left can be used to predict the right and the right can be used to predict the left. So in this case, we have that x minus a being a factor of fx predicts b, fa is 0, and b, fa being 0, predicts x minus a being a factor, which is a. So in this case, we can write that x minus a is a factor of fx if and only if fa equals 0. What this means is that x minus a being a factor of fx implies that fa is 0, and if we know that fa is 0, we can say that if x minus a is a factor of fx. This is an if and only if condition. The left implies the right and the right implies the left. So there we have it. This is the factor theorem and the converse of the factor theorem. So we can actually use these to solve problems. And often in the exam paper there is a question based on this. They'll say something like px has x minus a as a factor, and then they'll say something like given this fact and given that p dash x, the derivative of px, has x minus a as a factor, they'll say something like this. And then you can use the factor theorem that we learnt above to prove something based on this. In this case, what we are expected to prove, I remember this was there in the 2025 A-level paper, is that px has x minus a squared as a factor or something like this. Something like this was there in the paper. So questions like this come from this part of the syllabus. The factor theorem and the remainder theorem are quite important. Factor theorem is, I would argue, more important, but the remainder theorem is the more general one. The factor theorem is actually a special case of the remainder theorem. So in summary, to end this video, let's go over what we learnt. We learnt about how we define polynomials. We learned that a polynomial is a function where you have a bunch of terms starting something like this. We have a times a sub n times x to the n and a sub n minus 1 x to the n minus 1 going all the way down up to a sub 1 x to the 1 and a sub 0 x to the 0. In here we learned a certain bunch of words. The coefficients are all the numbers in front of the powers of x. The terms are the coefficients times their corresponding powers. The leading term is the term with the highest power of x. The order is that highest power of x. The leading coefficient is the coefficient of the leading term. And after using that, we then showed that if two polynomials are identical, meaning px identical to qx, which means that p of any a is equal to q of any a for all a in the real numbers. Given this condition, we proved that each of the pairs of coefficients of any power x to the r have to be equal to each other. We showed that a sub n is b sub n, a sub n minus 1 is b sub n minus 1, and so on. After proving that, we then started to do algebra with polynomials. We figured out what to do when you want to add two polynomials together. We figured out what to have to do when you subtract two polynomials. And then we talked about what happens when you try to multiply two polynomials together. And we talked about when you multiply a polynomial px of order n and a polynomial qx of order m, then the resulting polynomial will be of order n plus m. Here, this theorem. Then after that, we discussed how we define the division of one polynomial by another polynomial. We discussed how you cannot directly do it because we do not have decimals in polynomials, and instead what we had to do is take certain chunks of the top polynomial out from as the bottom polynomial, and by doing that we reduce the top polynomial down until there we cannot remove any more multiples of the bottom polynomial from the top polynomial. We made it analogous to division with remainders. We showed how you divide 17 by 5 with remainders, and similarly we applied that concept to here and showed how you can divide a polynomial px by a polynomial qx. We then showed three separate cases. One case where the order of the numerator was higher than the denominator, in which case we got a quotient of order n minus m and a remainder with order less than m. And we showed a case where in was equal to m, meaning that order of the top polynomial and bottom polynomial were equal. In that situation, we got that the quotient is order 0 or the quotient is a constant, and the remainder has order less than the order of the two polynomials. We then showed what happens in the case where n is less than m, or the top polynomial is lower order than the bottom polynomial, in which case we cannot actually remove even a single part of the top polynomial using the bottom polynomial. There is no number other than 0 that we can multiply the bottom polynomial by in order to get some amount of the top polynomial. So therefore, the quotient in this case is 0, and the remainder is simply the original function on the numerator. And then finally we talked about the remainder theorem and the factor theorem, how if we divide fx by a certain number x minus a, and we consider what happens when x is equal to a, we can say that f of a is r of a. And then as a special case of this, we consider what happens when the remainder is 0. And remainder being 0 is analogous to the function that we're dividing by being a factor of the top function. If px divided by qx has remainder of 0, that means that qx is a factor of px. And then we derived using this that if we have remainder 0, then f of a has to be equal to 0. If fx divided by x minus a has remainder 0, f of a is 0. And we call this the factor theorem. We showed that the factor theorem is true, and we showed also that the converse of the factor theorem is also true. That if f of a is equal to 0, we can then say that x minus a is a factor of fx. And finally, as a conclusion, I showed you a little notation method to write the factor theorem and the converse of the factor theorem in one line, saying that x minus a is a factor of fx if and only if f of a is 0. So this implies both ways. X minus a is a factor of fx implies fa is 0, and fa is 0 implies that x minus a is a factor where fx is some polynomial. And that is it. That is the conclusion that we have drawn. I also showed you an example of the kind of questions that they might ask from this. And now that it has occurred to me, tell me down in the comments if you want me to do paper discussions, like take some question from some kind of paper and then go through that, like walk through that question with you and show you the kind of solution that there is expected, and maybe the distribution of marks. So tell me if you want that in the comments down below. Give me any other feedback about my videos, if they're understandable, if there's something that I missed or something that more is needed. And that is it for polynomials. I think this video is longer than most videos, probably like 1 hour and 30 minutes long. So if you made it up to this far, thank you for watching and goodbye.